Yes.
I told you I'm very puzzled by all this system, this Zoom system. I have no clue how it works. And somebody asked me about that last time, and I simply don't know. Okay, let's do a share screen. And can you see my screen?
Yes.
Good, finally. Right? Okay. So let's finally start. So we're talking about the Higgs mechanism. So the official name actually is the Brute-Englert-Higgs mechanism. They all got the Nobel Prizes, you know. So the BEH mechanism. And we discussed about the idea of a hidden symmetry. And we saw that the implication in the context of particle physics, it has various implications, right? But the basic implication is to assume that we have a term in the potential V of I, 1/2 mu squared phi squared. So there is an extra term, which is of course a term of a self-interaction. But then the idea is that mu squared is actually negative. So mu squared is negative. Then when we plot, since lambda has to be positive for the potential to be finite, then when we plot the potential, then it looks something like that. Which means that we have several possibilities for a minimum. We can have two minima. The system will choose one minimum, and that is the symmetry breaking. So the physical system is, let's say here, can be in the other side as well, and that breaks the symmetry. That's called the spontaneous symmetry breaking. Now we develop it for several, in several steps. So the first step was a simple, a real scalar function, and then the next step was a complex scalar function. Right, when we wrote phi is 1 over square root of 2 phi 1 plus I phi 2. And then this 1D becomes a 2D, 3D, right? 2D becomes a, so you have sort of a Mexican sombrero type of shape. And that's of course invariant under global mechanism, but the idea of the Brute-Englert-Higgs mechanism is to make it invariant under a local phase transformation. BH, invariance or demand, invariance under local phase transformation. Right. Phi of x goes to phi prime of x is EIG some function chi of x, phi of x. Then we saw that this can be achieved by changing the covariant derivative, the derivative in the Lagrangian to a covariant derivative. That gives rise to a new vector boson, right, which we call the B mu. And then when we expand the field around the vacuum, so when we replace d mu into d mu, which is d mu plus IG B mu, and then the transformation of this new vector field, B mu goes to B mu prime, B mu minus D mu chi. Effects that we had previously, we saw that. And then when we expand the vacuum around the new vacuum, when we expand the field around the new vacuum state, right, phi of x is 1 over square root of 2 v plus eta of x plus I psi of x, right? And we put everything in the Lagrangian, we end up with a term it looks like minus lambda v squared eta squared in the Lagrangian, which is a mass term for the field eta. plus another term which have a scalar which does not have a mass. So, so we have the kinetic terms, 1/2 d mu psi, d mu psi. There's no mass. This is a massless boson. This is the Goldstone boson. Right? And so one corresponds to change of eta, along the change of the potential. And one, the psi, is along where the potential is fixed. The psi. Now, it turned out that if we simply write the Lagrangian in these terms, we end up with non-physical terms, right? We end up with a term which had a coupling between the Goldstone boson and the gauge field, which cannot be. And so we actually chose a gauge by choosing a specific gauge, saying b mu of x to, we chose b mu prime of x, which is b mu of x plus 1 over dv d mu t mu psi of x. Then we end up that the Goldstone boson was eaten, and the vector field B got mass. Now this choice of gauge is known as the unitary gauge. Right, so basically it's like choosing, it's similar to choosing phi of x to phi prime of x, which is E minus I psi of x divided by V, phi of x. And that gives us a Lagrangian of d mu eta minus lambda V squared eta squared. So there's a kinetic term and the mass term for the eta particle, minus 1/4 f mu nu plus 1/2 g squared v squared b prime mu prime mu minus v interaction. So the B boson acquired mass. We have a mass term for the B boson, which is GV. Right, so we ended up with a scalar field, a mass for the boson, and interaction term between all of them. And then we said that in this unitary gauge, there's no more massless Goldstone boson. It's been eaten and gave mass to the vector boson. That's pretty much as far as we went through on Tuesday. Any questions before we proceed to what happens in the real life, in the real world? No. Okay, the rest is actually, if you got the idea, the rest is pretty much following. It's just a little bit more complicated algebra. So the standard model Higgs, or Higgs in the standard model. So what we did so far was using the Higgs mechanism to generate mass for a gauge boson that corresponds to a U1 gauge, right? Local gauge symmetry. But in the model we have, right, we don't have a simple U1 local gauge symmetry. But what do we have? This you should know by now. Right, in the Weinberg-Salam model, what type of symmetry we use for the weak interaction?
SU2.
It's a U1
Yes.
right times SU2 left. That's the symmetry that we have, right? the symmetry in the Weinberg Salam, right, model. Right. So this is the local symmetry, right? Okay, this is the local, to be more precise, this is a local gauge symmetry of the electroweak sector of the standard model, right, to be more precise. So in this symmetry, we have, how many gauge bosons do we have? How many gauge bosons do we have in this symmetry?
4.
4, right? So what are these for? So we have, for the SU2, how many do we have?
3.
3, right? 3 for the SU2. Left. These are the W's. Right? W1, W2, and W3. And 1 for the U1Y, which is the hypercharge, right? So this is the B mu. This is the gauge bosons of the theory. Now in physics, what do we have for the physics? What are the gauge bosons that we're seeing in nature?
Photons.
Sorry?
Photons, no?
Photons, right? Yeah. And?
W plus minus and Z.
Right, W plus minus and the Z. How many of those have mass?
3.
Right, gauge bosons in nature, right? So 3 are massive, and 1 is massless, right? Right. So, how many Goldstone bosons do we need?
3.
3, right? Because each Goldstone boson, when it is eaten by one of those vector gauge bosons, it's going to give it a mass. So we need three Goldstone bosons. And then after symmetry breaking, we're going to have another massive scalar particle, right? This will be the eta, which is really the Higgs, right? So the simplest model that we can think of, right, must have 4 degrees of freedom, right? So 4 degrees of freedom, that is consisting of having either 4 scalar fields, or we can put them in the form of 2 complex scalar fields, all right? So the simplest Higgs model, I would say, requires 4 scalar field, which is 2 complex. For real. So in order for the scalar fields to break the symmetry, of course, then there must be charge under the interaction of the symmetry. So they have to go on non-trivial gauge transformation. So similar to the U1 example that we already had, right? We're going to give 4 scalar fields, and we're going to give them hypercharge Y. And in the SU2L, we're going to put them in isospin doublet, right? The same as we had previously. So this is for the U1, and for the SU2, we're going to put them in I equal 1/2, and I3 is plus minus 1/2. And again, the sign is going to be showing that the electric charge similar to what we did so far. So I'm going to write down the field phi as phi plus phi 0, which is 1/√2, phi1 plus I phi2, phi3 plus I phi4. Okay, so I put them as an isospin doublet. And of course, the phi plus and phi zero are there to remind us that there is a difference of charge of 1 in between the upper and lower part of the doublet, the same as we're doing usually for any doublet. Right? Now, from here on, we basically repeat the same calculation as we did previously. Right? So we write down the Lagrangian of this doublet. Right? Again, it's a complex scalar field. Now it's a doublet. So we have L is d mu phi. Now I have a dagger here. D mu phi minus mu squared phi dagger phi minus lambda phi dagger phi squared. The simplest as we can think. Right? Again, mu squared is more than 0 by assumption. And so the potential has a minima. Where phi dagger phi is, well, that's simply 1/2 phi1 squared plus phi2 squared plus phi3 squared plus phi4 squared is v squared over 2, which is just minus mu squared over 2 lambda. Right, that's the minimum of the potential. So far, I'm just repeating the same steps that we did previously, just slightly more complicated, that's all. And the reason I explained to you. And just because we need the 3 Goldstone bosons plus the 1 extra Higgs one. So we do the symmetry breaking, and then after the symmetry breaking, we want to have 1 particle to be massless. That's going to be the photon. And so the minimum of the potential, right, must correspond to the non-zero expectation value only of the neutral scalar field, phi 0. So the minimum, right, we're going to write it as 1 over square root of 2, 0 v of the potential, right, to get the photon massless, right? And then we're going to write it down as phi of x, expanding around the minimum, 1 over square root of 2, phi 1 of x plus I phi 2 of x. And then in the lower part, we're just repeating what we did. It's just the v plus eta of x plus I phi 4 of x. Right? Now, of course, after spontaneous symmetry breaking, we're going to end up with 1 massive scalar. That's going to be the eta. Right? Eta of x, this is going to turn out to be the Higgs, of course. What's going on here? Some strange things. And the 3 massless Goldstone bosons, which will end up to be the longitudinal degree of freedom that will give the mass to the W and the Z bosons. So, again, repeating the same calculation, we end up that phi of x is 1 over square root of 2, 0 v plus h of x. And then the low part of the doublet is identical to the U1 symmetry case. So we can simply copy what we did there, copy here. And so we end up that the mass of the Higgs is 1/2 m. Here it's still eta or h, it doesn't matter. Squared is just lambda v squared. And then the mass terms for the gauge bosons are going to be originating from the extra terms in the covariant derivative. All right, so the covariant derivative, d mu goes to d mu, which is d mu plus, we already wrote it down, I g weak tau dot w mu. These are the generators plus I g prime y over 2 b mu. Right? The full covariant derivative right, just go back to the part that we did it in the weak interaction. By the way, I don't know if you've noticed, but I put my lecture notes on the course webpage. Did you see that?
Yes.
Yeah, is that useful?
Yes.
It will before the lecture, before the exam, I hope. As I say, please keep them confidential. Don't spread them around. Now, the terms in the Lagrangian that generates the masses are, of course, the d mu phi dagger d mu phi, and I'm skipping the algebra because it's just an annoying algebra. And then there is diagonalization of the matrix of the W3 and B goes to Z and A. So we end up, again, the quadratic terms in the Lagrangian are 1/8 V squared G weak squared W mu plus W plus mu up plus W mu minus W mu minus plus 1/8 V squared G weak squared plus G prime squared Z mu Z mu. So since all the mass terms are of the form half m squared, then we got the masses for the physical. Since this is all the quadratic term, plus the kinetic terms, plus the interaction terms. Right, then we end up that the W mu plus minus, which are, to remind you, 1 over square root of 2 of W mu 1 minus plus I W mu 2, then the masses would be 1/2 G weak V. Right? That's because we have here 1/8 V square G weak squared, right? Which is 1/2 m squared. Right? And for the Z, which is here, so for the Z mu, right, which is G, I remind you, we did this derivation, G weak W mu 3 minus G prime B mu divided by square root of G weak squared plus G prime squared. Then we end up that M of the Z is 1/2 V square root of G weak squared plus G prime squared, G prime squared. And for the A mu, it is G weak prime, sorry, G prime W mu 3 plus G weak V mu divided by square root of G weak squared plus G prime squared. What is the mass? What is the mass, guys? Look at the Lagrangian.
Just 0?
0, right? There is no quadratic term for A in the Lagrangian. Right? We just end up with no quadratic term, meaning that the mass is 0. Right? There is no term that looks like A mu, A mu. Right? So the physical fields are the mixtures of the massless bosons associated with the U1 and the SU2 left local gauge symmetries. Now there is something which is much more interesting, because if we write down the ratio, we already did that, right? If we write down the ratios of the G, the two coupling constants, right, of the hypercharge and the weak, so G prime over G weak We write it as tangents theta. All right, and if we plug it in here, then we end up that the mass of the Z is just 1/2 G weak over cosine theta weak V. This is something which you can check with no time. But when we combine that result when we combine this result with this result, what do we get? What do we get? We get, come on guys, what do we get?
We get that we know the ratio between the MZ and NW.
The ratio of the masses. We don't know the exact masses because we don't know what is V, and we don't know what is the coupling constant G weak. But we do know that M of the W divided by M of the Z is cosine theta weak. It's quite amazing. Appreciate it, guys. All right.
I have a conceptual question.
Yeah.
It seems to me like to get that the A is massless,
Yeah.
requires just like a very lucky choice of numbers, like a good, like if you begin from the L and Y symmetries,
yeah,
to get eventually a massless boson,
yeah,
needs a coincidence, some kind of a coincidence, to get that the A does not couple to the Higgs, for example.
No. There's no coincidence. You build a theory such that this is a given.
So that's what I'm saying. You tune the numbers. G prime and GW are built to give you a massless A.
No. You can say the opposite. It's not the G, right? It's the you're going back to the idea of mixing between the electromagnetism and the weak, right? The electro-weak coupling, right? Remember, how did we get to this electro-weak coupling, right? It came out from the idea that we have a problem if we just look at the weak one, right? Because the weak only couples the left-handed particles, not the right-handed ones, right?
That's what I'm saying. Maybe I'll put it this way. Say you take an alien from another universe and show it the basic symmetries, only the SU3 of the strong force and the SU2 and L times U1 Y.
Yeah.
And you don't tell him the numbers. You don't tell him what are the values of G prime and GW, etc.
Yeah.
Will he be able to say that we will have eventually one photon which is massless?
No, the idea that the photon is massless is built in. You built it in such a way, you demanded the vacuum state to be such that you end up with one massless boson, which is neutral. That's why I chose it to be in the low side of the doublet, right? In the lower half of the doublet. So that I build down. Now here I don't know what is G prime and G weak. I don't know them. I did not measure them. The thing that I measure, right? I just measure I can measure theta weak, right? And that I do by scattering experiments, right? I know how many, what is the difference between, you know, the ratio of let's say, decay, as we discussed that a few days ago. If you have some beta decay, so I can measure where the electrons are going, right or left. So I can measure what is theta weak. And the amazing thing is that this tells me what should be the ratio of MW to MZ. It does not tell me what are the masses of W and Z, because I don't know what is G weak and I don't know what is V. I still have to measure them. But once I measured one, if the theory is correct, I know what should be the value of the other one.
And how can you choose if this whole idea is that you break a symmetry and that all the ground states are symmetric? How can you choose one ground state over the other?
I cannot. It's the same way as, you know, you cool down a you know, magnet below the Curie temperature, right? So if you're above the Curie temperature, all the spins are aligned randomly. When you go down below the Curie temperature, everything is end up a paramagnet, right? Everything is going to end up in one direction, but you don't know which one.
But it happens to be exactly the one that makes the photon massless.
No, it doesn't matter. No, it doesn't matter. If
So
you think back about this, I would simply define the photon to be another, you know, another of another of the four, one of the other three gauge bosons. I would always get one which is massless.
Okay.
Because I build the theory such that I'll have one which is massless.
And this one will always be also not just massless but also neutral.
Yeah, I require that. Yes.
Okay. Okay.
Okay. But this I get for free. I get the ratio of the masses, right? This, remember, right? You know, when people wrote that in the 1960s, the masses of the W and the Z were measured in 1983. That was 20 years later. They didn't know about that. They didn't even know about the Z until the 1973, I think. No, 1972. Right? They wrote the theory back in the 1960s, right? The Higgs, we said, was 1964. And it was put in the theory in 1967 as part of the theory. So we end up that the GSW model, right, is we have only 4 parameters, right? We have the 2 gauge couplings. So the GSW model, GSW, right? Glashow, Weinberg, and Salam. Glashow, Salam, and Weinberg. Right? It has 4 free parameters. SU2L times U1 Y, decay couplings, right? G prime and G weak. And then we have the Higgs potential and the vacuum expectation value. Right, we have then Higgs potential. So mu and lambda, which are related to V via V squared is minus mu squared over lambda. Right. And also to the mass of the Higgs, right? Because the mass of the Higgs squared, right, is just 2 lambda V squared. Now, if we know the mass of the W, which we do now, right, and we can measure the coupling constant for the weak, interaction. That is something which we can measure via the Feynman diagrams, and basically the decay rate of, let's say, neutron beta decay. Right, so measuring MW of GWV, right, and GW, the weak coupling, then we can get the value of V. That's 246 GeV. Now that doesn't tell us what is the mass of the Higgs, because the mass of the Higgs, we need to know what is lambda, which we don't know. Just that you know, we know today that the mass of the Higgs, we measure it, but there's no prediction of the Higgs mass before it was actually measured. It's 125 GeV. Cool. Let's proceed on, because we do need to finish at least that. I want to end up with discussing the discovery of the Higgs. What about
does this mean that lambda is like just almost exactly 2 or 1/2 or something like that? It seems like 125
no.
is almost half of 246, almost exactly half.
True. Yeah.
So lambda here seems like it might be very close.
1/8. Why?
Oh yeah, I did the multiplication wrong, but it's almost
here.
a very simple rational number. Do we have any explanation for that?
No, I don't know of any. All right, lambda should be 1/8 roughly. Okay, it's not exactly 125. It's 125.6, by the way, if you want to be precise. Okay, let's speed up.
246 is not exactly 250, but
yeah, okay.
They're still very close.
Okay. Mass for the fermions. Well, I just showed you how the Higgs mechanism gives masses to the gauge bosons, right? To the W and the Z gauge bosons. But the importance of the Higgs field in the standard model extends much beyond that, because it also generates the masses to the fermions, in fact, to all of the fermions, right? What is the problem, right? If we try to put masses to the fermions, right, in the simplest way, so if you write down minus mf psi psi, if we write, right, what is that? Then this is just minus mf, and then to write it down, oh sorry, it's a psi bar, it's a Dirac field. So then it's a psi bar right, psi left, plus psi bar left, psi right, right? But this, what's the problem with that? What's the problem? Why can't I simply do that? Actually did it without even saying anything, right? When we wrote down the spin half particles in the Dirac equation, I didn't say that there is any problem. I just wrote down the term like that. But now I tell you that there is a problem. You should understand what the problem is. So what is the problem?
Does it break the symmetry?
Exactly. It does not obey the SU2L times U1Y symmetry, because the psi L and psi bar right transform in different way, right? Right. This does not respect SU2 L times U1 Y symmetry, right? Psi L and psi bar transform in a different way. Right, right. So we have different electroweak charges, right? You know, psi left goes to psi left 1 plus I G weak alpha of x times tau. Right? And psi r simply goes to psi r. It's not part of this doublet, and it doesn't care about this electroweak. It just doesn't play. So this is not good. You cannot have such a term appearing in the Lagrangian of the standard model. Right. So this term, right, put a big X, it doesn't appear in the Lagrangian in the standard model. What do we have? What can we have? Instead, we do have masses for the fermions, right? We know they do. So we must have some term in the Lagrangian that represents masses. How can we get masses? We can do exactly what, sorry? Yeah, exactly. We can do exactly what we did. We can do an interaction term between the fermions, right, and the gauge field, basically the Higgs field. And when we have a symmetry breaking, then the vacuum expectation value of the scalar field is going to turn out into fermionic mass. Right? Exactly the same way as we did for the gauge boson. So rather, we add to the Lagrangian an interaction term between the fermions and the scalar field. Right, such that it is gauge invariant. We want to keep both the gauge invariance and the scalar field. So such a term would look something like LE is YE minus YE actually. And then we put the fermion. So it comes in doublet, neutrino E and E left. And then the field phi ER plus ER bar phi plus star phi 0 star, and then neutrino E and E left. Of course, this is for the first generation fermions, and the same for all the other generations of the leptons. Now the YE has a name. Anybody want to guess? YE. This term has a name. Y stands for Yukawa. This is a Yukawa coupling. This is a constant. It's a constant. Right. More precisely, we say this is the Yukawa coupling between the electron and the Higgs field. Right? There is couplings between each particle that has a mass and the Higgs field. Right? Now, after spontaneous symmetry breaking, right, the Higgs doublet, we get back with the doublet phi plus and phi 0 equal to 0 and V plus H or V plus H. So if you write down spontaneous symmetry breaking, it gives us phi plus and phi 0 1 over square root of 2, 0 V plus H of X. And then since we put a 0 at the beginning, that automatically means that we only get mass just to the electron, because everything that couples the neutrino is giving us 0. So the neutrino is not going to get any mass. Right? This is V. Right? This 0 here means that the neutrino, right? This 0 here coupled the neutrino, which will end up to be massless. All right. So that's going to give us that L is minus YE over square root of 2. And then we have V plus H, E bar left E right plus E bar right E left, which is exactly what we want. Right? This is exactly the term that we naively thought we'd put initially for the electron mass, right? But only for the fermion. But now what we did it in a gauge invariant way. Is that clear? Is that cool? Because you saw that we got something extra here, right? Okay, now two comments. So the Yukawa coupling is not something which is predicted by the Higgs mechanism. We don't know what it is. There's no way to know the rather. The way is to ensure that it's consistent with observations. That's it, right? So we simply write down, since we know what is the electron mass, then we simply write down that the YE is just square root of 2 ME over V to be consistent with ME, right? But then I can write down the Lagrangian, or the relevant term in the Lagrangian, right? This is minus ME E bar E, right? Minus ME over V E bar E H. Right? I have two terms here, right? I have the V, the vacuum, and then the H. The perturbation around the vacuum. What does it mean? What do we have here? It's damn beautiful. What is the first term? What is this term? Anybody? What is this term? Hi guys, I'm asking you a question. Please answer. Yeah? Somebody help me. What is this term? What are you seeing here?
That's just YE over square root of 2 V plus H.
No, this is just the mass of the electron. Right? This is this term in the Lagrangian, right? This is just the mass term for the electron. That's what it means, right? But now, where does it come from? It comes from coupling, right, between the electron and the Higgs field, right, and the vacuum. But now we also have another term, this term, right? What is that? What does that have? What does that term look like? How many particles appear here?
3.
3, right? We have 2 particles in the Higgs. So this term represents interaction between the electron and the Higgs boson, right? This is the Higgs field. This is the mass term. This is an interaction term between the electrons or electron and the Higgs particle. Right. Now, the coupling constant, right, is m over v. Right? Which means that we have a quite important predictions of all this theory. You know, I'm telling you stories, but these stories have predictions. Right? That means that the electron, in fact, any massive particle, must be coupled to the Higgs with a coupling constant that is linear in the mass. So the more massive the particle is, the stronger the coupling should be to the Higgs. Right? Or wrong? Yeah, you're with me? You're very quiet. Okay. So prediction. Right? All particles, all massive particles are coupling or coupled to the Higgs. Namely, they can interact with it, right? With the coupling constant, that is proportional to the masses. Yeah, I'm not exactly. It's all massive fermions because that's what I'm showing here. Now, the way I formulated it, this mechanism does not give any masses to the neutrinos, right? Of course, not a coincidence. This is by construction. I did it in such a way that the non-zero expectation value, right, of the vacuum occurs only in the lower part of the doublet, not in the upper one, right? Now, because the neutrino is the upper part, right? It's a multiplicity of the charge field. Now, okay, when we wrote this, when people first wrote that, neutrinos were thought to be massless, so there was no problem. Now today, we know that neutrinos do have masses, right? Now, there are two things. The masses of the neutrinos are extremely small, much smaller than anything else that we have. So one, it's not clear what gives them the masses. It's not clear if this is this mechanism or it's something else that gives them the masses. Because the coupling is so small, the masses are so small, it's really not clear. It's one of the open questions in particle physics. Now, I can just say that there is no problem giving masses to the neutrinos in this mechanism. The only thing we need to do is just to get the conjugate doublet. So let me just go over it quickly. So to give masses to the neutrinos, within this model, right? Can construct a doublet phi c, which is going to be formed as minus I sigma 2 phi star. So that's minus phi 0 star and then phi minus. So this is 1 over square root of 2 minus phi 3 plus I phi 4 and then phi 1 minus I phi 2. And then use the same properties of the SU2 and then the conjugate doublet phi c is transformed in exactly the same way as the doublet phi. And then a gauge invariant mass term for the neutrinos will look something like L neutrino, a gauge invariant neutrino mass term. L neutrino is just plus y, but it's going to be a different coupling. So it's going to be y neutrino, and then neutrino bar, E bar left, and then minus phi 0 star, phi minus ER plus Hermitian conjugate of that. Then, of course, after symmetry breaking, we're going to get that the minus phi 0 star and phi minus going to 1 over square root of 2 minus V minus H of X 0. So we get essentially similar to what we did with the electrons, just using conjugate, doublet, and that's it. Okay. Since the Yukawa couplings are not known and are not predicted by the theory, it's just something which is being measured. Okay. Now, so what I showed was how to give the masses to the first generation of the leptons. Of course, you can go to the second and third generations and it all looks exactly the same. And then if you want to do it for the quarks, there is a slight complexity. Again, it looks very similar, but again, the structure is a bit more annoying. Why is that? Why can I simply repeat what I did and rather than neutrino and E put an up and down?
Because they have both have masses. One
No,
mass.
that's no problem.
Because there's another symmetry involved.
Yes, yes. What is that?
The SU3, was it? The strong,
okay.
the symmetry of the strong.
What I meant is something simple, right? We have a difference between the mass basis and the interaction basis. Remember, we have this CKM matrix, right? So we have a different quark masses, so it's similar, but there is a difference between the mass basis and interaction basis. Right. So if we just do exactly as we did for the leptons, we're going to end up with masses, but in the interaction term, and we want masses in the mass term, in the mass basis term, right? So basically, the only thing we need really is to have a mixing. So we want the Yukawa coupling basically to mix the quark generations, right? So what we need is that the Yukawa coupling mixes the generations. So basically, in the interaction basis, we're going to get that L, let's say down, is going to be minus Y down Ij. The Ij would stand for the different generations. Then we'll have U bar, D bar, IL, phi plus phi 0, dr, but this is going to be d prime of r, j plus Hermitian conjugate. And the same for the up. Y up, Yj, U bar, D bar, I left, and here we'll have the minus phi 0 star and phi minus U R prime, J plus Hermitian conjugate, where D prime, U prime in the interaction basis, and I and J are the different generations. Of course, there is a summation here, right? And the Yukawa couplings now become matrices. Right? We have two matrices. You know, Y up and Y down becomes 3 by 3 matrices that mix the generations in the interaction basis. So Y, Ij up and down would be matrices of Yukawa couplings. And of course, after the symmetry breaking and in the unitary gauge, we end up with phi plus phi 0, again, what we had, 0 v plus h. And then the final, the quark mass is going to be L quark, right? It's just L down plus L up, minus 1 over square root of 2. Now it's going to be a bit more complicated, but there's nothing much, just some ugly algebra. Y down ij d prime bar I L b plus h d prime j r plus y up ij u prime bar I L v plus h star u prime r j plus summation conjugate of all their. So again, similar to what we got for the leptons, we have one mass term, the V, and a second term which couples the quarks to the Higgs. Right? And in the mass basis, this have a diagonal form. So in the mass basis, these have a diagonal form, right? L quark is just minus y d I d bar I L v plus h d r I minus y u I u bar I L v plus h star u r I. So again, it's just some algebra which can be quite confusing. So I don't want to confuse you for no good reason, right? So the y's, yi up and down, these are just the Yukawa coupling constants in the mass basis, and the d's are the, everything is written in the mass basis. And now we have just a summation over the generation I. So again, it doesn't tell us what are the masses, because to know the mass, we actually need to know the Yukawa couplings. But that gives us a lot of information, because that enables us. The theory have a very, very strict prediction that you already wrote, right? That all the particles should be coupled to the Higgs. So if we have a Higgs, how should the Higgs decay? Right? If you got the idea, to what particles can the Higgs decay?
Any massive particle?
Any matter particle, that's true. All the standard model particles. Right now, but the proportionality of the couplings to the mass of the particle, because the coupling is proportional to the mass of the particle, right? Then what is the largest branching ratio? What particles do we expect the Higgs to decay most to?
The most massive ones?
The most massive ones, very good. All right. So the largest particle that the Higgs can decay to is the bottom one, because the top is too heavy. So the branching ratio of the Higgs to decay into bottom, small b, b plus b bar, right? This should be nearly, it's 57.8%. Nearly 60% of the times, we would expect the Higgs to decay to the BB bar, right? The branching ratios just generally right? B branching ratio of Higgs decay into the B plus B bar to the branching ratio of the Higgs decay into the C bar to the branching ratio of the Higgs decay into the tau plus tau plus minus, right? So leptons. This should be roughly 3 times mass of the bottom to 3 times mass of the charm, squared, of course, because there are 2, to mass of the tau squared. Why did I put the 3s in there?
Colors.
The colors, because the quarks have 3 different colors. That, by the way, measuring this is another way of measuring how many colors there are. How many generations there are, sorry, how many colors there are. This is for the 3 possible colors. Right. Now, one comment is that the masses, remember, we didn't really speak about that. Remember the issue that we kind of mentioned at the beginning, the idea of a running coupling constant. So that means the coupling constant is a function of the energy. And so that means that the masses are functions of energy. So when we do these calculations or the theoretical predictions, we should know what energies we are looking at, because higher energies, meaning that the masses are somewhat different than the masses of the, zero energies. Okay, so in the LHC, the Large Hadron Collider, we first have to produce the Higgs, because the Higgs is not just there hanging around. Oh, sorry, just before that. Okay, just put a note that the masses depend on the energy. That's called the running coupling constant. Which, as I anticipate, we didn't really have time to discuss. So the mass of the Higgs is 125 GeV. Now, another comment is that there is one more important branching ratio, is the decay of the Higgs to the W boson. Now, although the Higgs is not as massive enough, so you have the M, so mx, let's just write now, mx is 125 GeV. Now we can decay m Higgs is smaller than 2 times mw. Right, the W boson is something like 80 GeV. But the Higgs can decay into 2 W's, provided that one of the W's is a virtual particle. So that's why we say Higgs can decay. Higgs goes to W plus W star. And the star is to remind us that this W is a virtual particle. So it's off the mass shell, right? W star, virtual particle of the mass shell. Which means that the Q squared is smaller than mw squared, which means essentially that this W by itself is going to decay pretty quickly into something else, right? So, but that essentially meaning that the decay amplitude is going to be suppressed. Now, Q squared is smaller than mw squared. The decay amplitude will be suppressed. Right. Another comment is that the Higgs can end up decaying into photons and gluons, namely into massless particles. But of course, it's not going to do it directly, but via a loop of quarks, such as the top quarks, or the W boson. So Higgs can decay into massless photons or gluons via a loop of virtual top quarks or W bosons, right? So the relevant Feynman diagrams will look something like that. So the Higgs is denoted with a dashed line. So it can make a loop of virtual top quarks. And then the top can decay into gluons or into photons. And essentially, the W can also decay into photons, of course, not into top, or not into gluons. Right? These are allowed. Now we have a branching ratio. So the branching ratio, just to give you kind of concluding, right? So the branching ratio for Higgs into the B bar is branching ratio. This is 57.8%. The Higgs going into W star, this is 21.6%. The Higgs going into two gluons is something like 8%. Higgs going into two taus is 6%. Higgs going into the charm, anti-charm, that's 20%. And to two Z's, 2.7%. And to two gammas, it's only 0.2%. But it's there.
These numbers sum up to more than 100%.
Then must have some mistake somewhere.
I think, right? There is 50, 20, 20, and yes, that's too much.
That means that I have some mistake somewhere. I have to check it out.
We all have access to PDG.
Well, check it out in the PDG. What did I do wrong there? That is true what you say, but I have to check out the numbers. I don't have it right now with me. Possibly there is a typo in one of them. Maybe it's not at 22.9, but only 2.9% here.
Perhaps WW star doesn't count.
No, WW star
does. It does count. It doesn't count as something.
Maybe you're right. Okay, I don't remember. I have to check it out.
Never mind.
I have to check it out. I simply don't remember. Okay, this finally gives us the possibility to discover the Higgs. Now that we understand what happens, right? So the Higgs was discovered by the Large Hadron Collider, the LHC. This is the largest and the most energetic, or the highest energy particle collider ever built by man. And it's also the highest luminosity collider ever built by man. So it's a proton-proton collider, LHC, Large Hadron Collider. That's in CERN, of course. It was discovered by several runs that were made in 2011 and 2012. So the winter of 2011, 2012, until the summer of 2012. The center of mass energy, square root of S, was 7 and 8 TeV in these runs. And the discovery itself was done by 2 independent detectors so that they can check it out each other. So 2 different experiments. One was called the Atlas experiment and the other one was called the CMS. CMS is for muon, compact muon, and I don't remember what is the S at the moment. Compact muon something something. Now, I didn't really have time to discuss with you properly about the detection techniques, but generally, since all these particles, especially the particles that interact via the strong interaction, they are very short-lived, we don't really see them in the detectors. What we see is their outcome, which is mainly muons and pions. That's mostly what is really being observed there. And the publication of that was done in summer 2012. This is the Atlas and the CMS detectors. Now there are many ways of producing Higgs in the LHC. The 2 leading ways, of course, it's a hadron collider, so it collides quarks essentially. So what we have, again, since the Higgs preferentially couples to a mass, then the largest cross section for producing the Higgs is via gluon-gluon fusion. So production of Higgs goes something like that. So you have 2 quarks collide, Q prime, and then they exchange gluons, which have the 3 loop of the T particle, of the T quark, which then produces the Higgs. The other way of doing it is via the W's. Q prime, and then W, and they both produce the Higgs. But this is the leading one, right? This one is, these are the 2 most important ways of producing the Higgs in the CERN. The via PP collision, right? The cross section for the gluon-gluon is something like 20 picobarn. So sigma here is of the order of 20 picobarn. And for the WW star decay, it's much smaller. It's about a factor of 10 or even more smaller. That's about less than 2 picobarn. The number I have is 1.7 picobarn. Now, there are other processes, but their cross sections are much smaller than those 2. So these are the values that we're talking about. So the total cross section is of the order of 20 picobarn. Now, once you produce those, then of course you need to know that you produce the Higgs, and the way to know that is to look at the decay of the Higgs. But of course, one need to discriminate to tell you that what decays was actually the Higgs, because what you have here is really proton-proton collision. So you have many multi-jet final states that you can have. So to discriminate the Higgs, to detect the Higgs, or to identify the Higgs, one needs to discriminate the decay products. Of the Higgs from the background. Now there are plenty of background things which originate from this PP collision that are there. So does any of you have any idea, let's say if you got an intuition, what would be the most sensitive decays? Or the most sensitive distinctive final states?
To make sure I understand the question, you ask what should we look for to be most sure that we see a result of Higgs and not of something else?
Yes. When you realize what happens, right? So you take two beams of protons, they collide with each other. A lot of jets, a lot of things happening there. Now we're looking for the specific indication that told us that there was a Higgs produced there. And what we're seeing is the outcome of decay of a Higgs.
You want it to be very massive.
No, you won't see the massive, right? Because if you see the T, for example, right, it's going to decay immediately. What would be a clear indication that what you saw comes from a Higgs and not for something else?
Something that results from a pair of two massive particles, say top and anti-top?
No. Because you get many of those when you're colliding, via the QCD processes you have there. The Higgs give you something which is unique, relatively unique. No clue? We're having quarks here, right? Okay, so the quarks would mainly interact via the strong interaction. So what we're actually looking for is interactions which would be via the weak interaction, because there the ratio of the signal to noise is going to be the highest. So although the branching ratio for that is among the smallest, this is still what we're looking for, because then the background is going to be even smaller. So what people look for is the decay of the Higgs for the final states. The most sensitive searches, search involve H goes to gamma gamma, H goes to Z star, which follows into 4 leptons. And H goes into W star, which goes into electron, neutrino, muon, and neutrino. Neutrinos cannot be detected. The cross-section is too small. We won't detect them in these detectors. Now the branching ratios of all this is very low. It's only a few percent. But the background noise is the minimal. So that's why it's being looked at. Now, okay, now let me show you. Okay, so this is the results. I thought it would be bigger. I can make it bigger. So these are the results. These are the 2 experiments that I'm talking about. This is the Atlas. This is the CMS. The left one, the red one, is with the Atlas. This is the decay of the H, as you can see here, H into Z star goes into 4 leptons. This is the Higgs, right? This one. That's what we're looking for. This small light blue axis here. So expectation was to 4.9 events as the background between this mass ratio of 120 to 130 GeV. And the outcome is 13 events. So there's 13 events here, and that's enough to claim a detection by more than 5 sigma. The number in the CMS, again, this is the CMS. You can see here it's the same, 120 to 130. It's 3.8 event is the expected background, and 9 events were detected. Again, that's enough to see. Now there is also another detection. It's the Higgs goes to the gamma photons. That's, I hope I didn't confuse you. No, I did not. I don't think I did. This is for the 4L. And again, it was found that the analysis gave a statistically significant result, you know, significant enough to get Peter Higgs and Englert Brute, I think, as well, the Nobel Prize. Okay. I think we ran out of time, although we started a few minutes late. Yeah, I also have, I don't have it, I didn't put it here. I can't. Yeah, I did put it, but I didn't, I have it in my notes, but I didn't move them down to my laptop, to my iPad. The photon detector, right? The photon pair. I don't know if you can see, if I can try to put it to you. I don't know if you can see anything here. There is this, this is for, I said there are two ways of detecting. One was for the 4Ls, which I just showed you. The other one was for the photon. You see this small bump here? Can you see it? This is the small bump. This is the photon, excess of photons, right over here. And this is in the Atlas, and this is in the CMS. You see there is an excess of photons here. There is a small bump, barely seen. This is excess of photons, which is, again, enough to claim a detection. So I'm sorry I didn't download it so you can actually see it, but you can, I think you can even find it in the Wikipedia. When I did my homework, you know, preparing that, I think you can find some data in the Wikipedia. You might even see these in the, you know, just to search for Higgs or finding Higgs in the Atlas or the CMS, and you'll see immediately these results. Okay, so we had two detectors independent, finding the Higgs via two independent decay channels, and they were all consistent with having the same mass, all consistent with having the same coupling, and therefore there is a claim of detection, which pretty much completes the, you know, this whole beautiful story that I'm telling you about, all these great Lagrangians and all these symmetries and all these, you know, stories about gauge symmetries. It all boils down to these miniature plots, which actually show you that there is some truth in it. Okay, any questions? No, well, we ran out of time and it's the last lecture. It's the last time of the semester. So I want to thank all of you for staying here and being here the whole semester. I want to remind you, if you haven't put down your teaching evaluation form, then please do that. That helps, you know, helps improving. If there is things that need to improve, that helps, you know, give feedback. If it's a good feedback, of course, it's always welcome. It's always helpful. And if it's a bad feedback, it's also useful. So please do that. The exam. Now, I know it's the first time that this course is given. Well, at least the first time that I'm giving this course. So I know that you don't have much to practice about. So I try to make something which will not be particularly hard. I can tell you that the exam is going to contain 3 questions, and I try to cover various topics which we talked about during the semester. Things that you've been practicing in your homework, but also things that I've discussed and we didn't really practice. So, but of course, I don't expect you to invent the physics during the exam, but I do expect you to show that you understand. Now it's going to be a closed book exam. I'm going to give you all the information you're going to need in the exam sheet. So if there will be something about a specific particle, the composition of the particle, its parity, etc., you're going to have it on the exam sheet. So you're not going to need to use any reference, any note or anything. Everything is going to be given there. I'm nearly tending to think that the exam is too simple. So I wouldn't be surprised if you just end up with the exam after, it's designed for 2 hours, but I wouldn't be surprised if you end up with the exam after much less than that. But you do require to do some thinking and to show that you understand the basic concepts, and you can do some basic, but really basic calculations. If you did your homework by yourself, you shouldn't really have any reason to worry about the exam. Yeah, that's pretty much what I have to say. 3 questions. They're supposed to have a few parts each question. So it will make it easier for me to grade and easier for you to see how much you're going to get for each section. 1 short question and 2 somewhat longer questions, but really not particularly long. And I really tried not to keep it particularly difficult. Put it like that. When I wasn't sure, I preferred not to give you something that I thought that could confuse people. Having said all that, you do need to show that you understand what I was talking about during the semester. All right. Any further questions? Comments, concerns, anything?
Thank you very much.
Thank you.
Thank you very much. It's been a pleasure. And I wish you all good luck in the coming examination period and your studies in general.
I have one question. Do you have access to exams from parallel courses in other universities?
No. I try to do that myself. If you get some access, give them to me. It will help me for the next time. So I had to think of some questions myself.
So if I do get access,
yeah,
can I send them to you and you tell me if it's in the general direction for the exam?
Yes, but I try to. I mean, I did get access to the tutorials that, so some of the problem sets that were given in previous, in other universities. That's how I based the problem sets that you got for home. But I did not get access to any exam. So I tried to base it on pretty much what I gave you during the homework. But yes, it will be actually quite good if you get some exams from other universities and you can send them to me. I will be grateful.
Okay.
Okay. Yeah, and what else can I say? No, nothing, I guess. Thank you very much. Good luck. If you need me, the exam is going to be via the Moodle. As far as I understand, I still need to check it out, but it's going to be, I'm just going to post it on the Moodle. So you'll get it, I think it's in the 8th of February. I'll check out the exact time. If any of you have any, if you're allowed to have an extension of whatever kind, please let me know in advance. Of course, I obey the university rules. So everybody that has a right to get extension will get it. And you just on the time, on the exact time of the exam, on the exact date, you just see that appearing in your in the module under the exam. As I said, exam is going to be closed books, so you're not supposed to use any kind of help. You're not supposed to use the internet. You're not supposed to use any textbooks or anything. All right. All right, then I can do the stop sharing. I thank you very much for being here, and I hope you enjoyed, and I hope you learned something.
Thank you very much.
Thank you.
Thank you.
All right, bye-bye.
Bye-bye.